Hello and welcome. In this video, we're going to be taking a look at how we're going to decommission an electric motor. And decommission, we're going to take it and we're going to put it into storage so that it's going to be operational in good peak form for when we need it again. Where we use this is in like industrial applications where we have constant change for mining operations, for pulp and paper, for the auto industry, where we have to do shutdowns for a period of time and then bring them back online. That can be very detrimental to a machine if it's not cared for properly. So, what I mean with that is that as it's sitting there, if we just unplug it, it's going to condensate on it. Condensation on that raw metal, especially the irons, are going to degrade that metal. We're going to create the oxidization. We're going to ruin these machines. So, how we can prevent that is by making sure that they are heated to some degree, a little bit of heat. We don't want them to be hot enough so that they're going to be melting the insulations off, but we want them to be warm enough so that it's going to keep that moisture at bay or not to accumulate on it. Much like how you would store your motorhome or something like that, getting rid of the moisture. So in a normal operation, if you take a look at what's on the right or the left hand side here, we have a cutaway of our motor. Okay, an actual drawing of our motor. Inside of that drawing, right in here, we've got our stator windings, and on the inside of here, we've got our rotor. The rotor reacts to the magnetic action of that stator. And so the way that the stator works is by using an AC supply, and please forgive me, my drawing ability is not great, but our three-phase power supply, we have an oscillation positive to negative on each phase times 3. In my simplistic drawing over here, I've got a stator that has just one winding for each phase, just so we can sort of see that what's happening. In the beginning here on, let's just choose phase B, the black phase here. It's in a positive cycle at the very first half cycle, and then it goes into the negative. So for the first bit, it's positive, negative, and then the second half rotation, once it hits that 0 mark, this now goes from negative to positive. Okay, it's just rotated and it's just flipped 180 degrees. In that way, we now get a magnetic shift. This was, let's just say this was north, that will now become south, knowing that the left hand rule for magnets and the around a coil would indicate that we are going to have a change in polarity. What ends up happening is that we create a synchronous magnetic field that's going to be circling inside of here, and that's magnetic rotation. We don't want that. If we're putting this into cold storage, we do not want this motor to run. We want it to be efficiently stored so we're not burning excessive energy, and we don't want wear and tear. If we reduce that voltage to this motor in an AC, we're going to be burning out that motor too, because it needs to have voltage and hertz relationship maintained, that ratio. Can't do it. So the simple way of doing this is to create we're going to disconnect that motor from its AC supply, and we're going to attach it to a constant DC supply. When we do that, now we remove that magnetic oscillation or that field. It doesn't happen anymore. This will become, let's say, north, and it will stay that way. Okay, it's now DC, but it's going to have a very small value. That rotation is not going to happen on that rotor. And when we have that small amount of voltage, we are now going to have a current flow through this. With that current flow, we can now see P equals I squared R. We have resistance in those conductors, albeit a fairly small one, but we're going to have a current flow through them, and that power is heat. Okay, that is going to be what's generated here. When we have that heat, we're going to have that on those conductors, just a little bit. It's all it needs. And that's going to transfer into the stator metal itself, creating that heat. We can do that with one winding, or we can do that with all windings, whatever we want. We just need a DC power supply to be able to sustain this. Now, that DC power supply needs to have fairly low voltage to make sure that our current is going to be limited. Okay, it will have to be calculated out in advance. Now, there are many ways that we can do that AC to DC. We can throw that through a rectifier. We can also put that through something that's already pre-established and pre-built. We can throw it through a welding machine. A welding machine on a low setting. So a welding machine already is a rectifier. It's a controlled rectifier. It's controlling the amount of voltage current output. If we have that in the low setting, it can be our DC supply that can work for this. It doesn't have to be a welder. It's just an example of what it could be. It could be anything that will provide you with that DC current. We don't want to be blowing heaters through these things. We don't want to do any of that because it's inefficient and it doesn't work and we're going to get too hot. We just want a small amount of current through these windings, keeping the heat where it needs to be. Hope that helps.